Hi everyone and welcome to my YouTube channel. So we're continuing our EGMO playlist. In the previous videos, we've finished discussing the part 1 of the EGMO book, Euclidean Geometry for Math Olympiad by Evan Chen. So like part 1 was like the fundamentals one. It was all about angle tracing, circles, lengths and ratios, and finally we discussed the assorted configurations. So basically, once you're done with this, then you are familiar with all standard geometry ideas, and you're actually ready to solve like even hard problems, as we did with assorted configurations. Yeah. Then, after we're done with this chapter, with this part, we're going to start our second part, so analytic techniques. So this part is basically all about bashing. So basically we have 3 chapters: computational geometry, complex numbers, and barycentric coordinates. These techniques are basically like the idea is to transform your geometry problem into some algebra. That's like we can say the basic idea of these chapters. So this is actually really powerful. In many problems, you can just get rid of the geometry of the problem, like the constructions and these kinds of stuff, and they instead just try somehow to transform it into some like algebra, maybe some equations or something that you just need to prove with some algebraic tricks. Basically, chapter 5, which is like this video, is about trig bashing, so like it's about trigonometry and Cartesian coordinates as well. The 6th chapter, next one, is about complex bashing, so how to use complex numbers in order to bash the geometry. And the 7th one is like using barycentric coordinates, which is like a very sweet and powerful bashing technique, like also for the same reason. Of course, like the third part is still like let's say you transfer back to the first part, but we just of course learn like new techniques like invergent, projective geometry, complete quadrilaterals. So right now we're going to start with our second part, and in this video we'll be just discussing computational geometry. As we said, the contents are Cartesian coordinates basically, and trigonometry. The main focus will be on trigonometry. So I hope you guys excited for the video. So what are you waiting for? Let's get started. Our first idea is Cartesian coordinates. We want to have a look at these. Of course, you're familiar with these from school basically. We all learn Cartesian coordinates, just the xy, like the x-axis, the y-axis, and like how to simply find, like the basic things. Let's just like say, just remember together what we can find. So let's say we just have like y-axis here and the x-axis here, and of course we have the origin here. And then of course if you have any point, given point like P, it has like an x coordinate xp and a y coordinate yp, and of course we know that like if you just drop it here and drop it here, then this represents the xp and this is the yp right here. And of course we know all the properties for it, like for example the distance formula. So if you just have 2 points, maybe like let's say AB, what's the length AB? So AB is simply the square root of XA minus XB squared plus YA minus YB squared. So this is the distance between 2 points. Of course, even if you have 3 points, like if you have a 3D, not 3 points, just like if you have 2 points but on 3D, then also you're going to have the same thing, but you're just going to add plus C, right? Plus CA minus CB. Anyway, right now let's focus on our Euclidean geometry. So yeah, this is the distance formula. Of course, if you have like if you want to find the midpoint M of AB, then you just like say XA plus XB over 2 ya plus yb over 2. And of course you can find like any ratio if you just have segment AB, like if you have like 1 to 3 or like the midpoint or whatever. You can always like figure it out by just creating like just knowing the ratio, and you can figure it out. Okay, so you know all of these. What do we also know? Yeah, of course, so we also know how to do equation of a line, right? Equation of a line. So given any line, you can either write the equation of a line like this: ax plus by plus c equals 0. That's like the first form, or the second form, which is y equals mx plus b. And this one works actually for any line except vertical lines. Why? Because vertical lines do not have a slope, right? Slope is undefined. So just keep that in mind. So this works for non-vertical lines. Yeah, usually like we just stick to this because it's much easier. And of course, as you know, m is just the slope of the line. P is the y intersection, like the intersection with the y axis. So for example, if you just have here like 1, if you have this line and this is 1, then P is 1. You can easily see, because if you plug x as 0, you're just going to get y equals P, right? So yeah, that's it. Okay, and of course, generally speaking, if you want to find a slope, then you just find delta y over the delta x, right? So y2 minus y1 over x2 minus x1. So if I just give you any 2 points, and I told you find the slope for the line passing through these 2 points, then you immediately just do delta y over delta x. You find m, and then you figure out p, right? Because now you figured out m, so you just have one more variable, which is p, that you need to find. You just plug one point and you find out p. Yeah, so it's very easy for us to find like equation of a line. And of course, if you want to intersect two lines, then it's easy. You just, let's say this is L1, this is L2. You just do the, let's say L1 was y equals m1x plus p plus p1, and L2 is just y equals m2 x plus p2. You just equate these, figure out x, and figure out y, and you figure out like this point here. Maybe let's call it capital P. So it's also easy to intersect two lines. What do we also know? Yeah, we also know that parallelity, right? If you have two parallel lines, L1, L2, they're parallel. Then of course, two lines being parallel means their slope is the same, right? So just saying L1 parallel to L2, that's equivalent to saying M1 equals M2. So yeah, that's actually it's very easy to check if two lines are parallel in a question. Same thing for perpendicularity. Like to check perpendicularity, we just need to check that the product of the slopes is -1, right? Again, remember that one of them should not be vertical. If you have like vertical, then there is no slope there. So yeah, you can also like figure it out from here. So perpendicularity is very cool with Cartesian coordinates, and parallelity as well, and intersecting lines. Dropping perpendiculars also is easy. Like if you just have a point here and you want to drop a perpendicular, then you can just do the same thing, right? You have the equation of this line, you just figure out m, you just figure out the slope for this, and then you know what's the slope of this, and you know 1 point, so you're done. You can figure it out. You can figure out the equation and just find this point. Yeah, so these are basically the main ideas. Let's see, did we miss anything? Yeah, these are the basic ideas. Of course, like in the book, you will see two, let's say, theorems that are actually quite handy. Let's discuss them. The first one is called the show-list formula, and the idea is to find the area of a triangle. So let's just say you have a triangle ABC, and of course you know just A is XA, YA, B xb yb and c xc yc. So it turns out that the area can be written using this determinant xa ya1 xb yb1 xc yc1. Now, of course, you're going to ask me what exactly is a determinant. The determinant, actually, if you're not familiar with it, you can go to the appendix at the end of the book, and you can check. It has nice properties. We're going to discuss these properties in details in the, I think, 6th chapter, which is the barycentric coordinates, because all our barycentric coordinates is going, or everything is going to be about a determinants. Right now we will not discuss them in details, but I'm just going to tell you how to calculate it. So the very basic way is just to take the product like this. Take this product here. For example, now if you just multiply, then it's just xa yb, right? And then you do the same. You just go up. Now you take this diagonal like this, right? You just add it. So ya times xc. And then you move on. So this next one is this. So it's going to be xbyc. Now, okay, we're done, because now we're going to get back to this. So now what do we do? Now we go and say minus and open parentheses, and now we go the opposite way. So right now we're doing it like this. Now we go like this. So now it's xc yb, and we continue like the same way. We go then like this, ya xb, and then we just add xa yc. I think now you got it, like you got the pattern. So yeah, right now we have calculated this. So this is basically the area for the triangle. Now, of course, this might be negative, so you need to take the absolute value. However, this actually gives you the signed area. What exactly is a signed area of a triangle? So, you know, like we just can have an order. Like, for example, let's say this is the triangle A, B, C. If you apply the formula like this, in this order, A, B, C, then you're going to get the signed area. To figure out what's the signed area, let's look A, B, C. They're like this, right? Is this clockwise or counterclockwise? It is counterclockwise, right? So it's positive. So here the answer is going to be positive. However, let's say you plugged it using ACB. Now ACB is going to be like this, and hence it's clockwise, and hence it's negative. So it's just going to be negative. So just like for you to know, if you really don't care, just take absolute value. However, if you care, then just know that this gives you the signed area, and you can figure it out. Again, like we're going to discuss the properties for the determinant in the like in a later chapter, barycentric coordinates. But now you might ask me, like, why exactly do we care about this? Well, of course, the easiest let's say situation is literally if they ask you find the area of a triangle, then of course you just apply this. However, this also has another use, and the idea is, what if you have collinearity problem? Let's say you want to show A, B, and C are collinear. Well, of course, like you might say, that's easy to deal with collinearity problems. We just, like, let's say A, B, C, to figure that they're collinear, you just do this: YB minus YA divided by XB minus XA. So that's basically the slope for MAB, right, for this line. And then you figure out MAC, which is just YC minus YA divided by XC minus XA. And then you just figure out that they're equal. Like, just check they're equal. If you know they're equal, then you're done. Because they are parallel, and if they are parallel and they share A, then they're collinear. So yeah, definitely that works. However, in some problems, you're going to have, let's say, like the question has 3 points, and each point, like this, is kind of corresponding to A, this is to B, and this is to C. So sometimes, like, you have this symmetry of a question. Like, for example, you have originally a triangle, and maybe then you drop 3 altitudes, and then maybe you take 3 medians and stuff like these. And then here you define some point, let's call it maybe xa, and here xb, and here xc, and then like you'll struggle a lot to figure out xa. Okay, you'll find it at the end. It's going to be something maybe very ugly. Then you'll find also xb and xc by symmetry, like you don't need to do all the work for them. Then actually if you go and check this and check this, then you're going to like suffer here, because you need now like to put all of the ugly yb and ya and subtract them and do the same thing here. Of course you can do this, it's totally fine, but we have this nice idea of the area of ABC should be 0, right? Because they are simply collinear, they don't form a triangle. So you can actually do a determinants here. So you can just plug one point here and the other points as well, and you will see actually that determinants have lovely properties that are very useful. You can try to play with the points somehow and just simplify. You will see again this in the arithmetic coordinates chapter, that sometimes you will have very ugly like points. However, using determinants properties, these actually will be very nice. Like you'll be able to simplify that. So yeah, again, if you run into this situation, then probably if you just use the Shorley's formula for that, for collinearity, just make sure that this is 0, then it would be easier than doing this. Anyway, for the easier problems, then you can just stick to this idea that we're already familiar with. So that's for the Shorley's formula. The other like theorem that's mentioned there, it's the point distance. Point line distance formula. So what exactly is this? So let's say you just have a point here. Let's call it A, maybe xa, ya, and you just have a line here, a line L. Let's say it's ax plus by plus c equals 0. Okay, probably I should say p. Yeah. Then what we're interested in the distance from this point to the line. So this, how to find this distance? Let's call it d. Of course, like you might say, wait a minute, we can simply just create the equation of this and figure out this point and then just apply the distance formula for like this point and this point. Of course you can do that, but it turns out that there is just simply a formula for that saves you the trouble. Of course you might tell me that, wait a minute, usually we have the line is like y equals mx plus p, but come on, like it's not a big deal. Just like move them to the to one side and just write them like this. So do not worry about that, you can just transform it into this. But after you transform it, I'm just going to write immediately. So the distance from P to L is the following. So first of all, just to help you memorize it, you have this is the equation of the line, right? Just plug this point inside it. What do I mean? I just mean write the equation of the line and plug the point inside it. So x is xa, y is ya. Okay, right now it's easy for you to remember. Just plug the point inside the equation. But then this can be negative, right? So we should have absolute value. Okay, so far so good. Now you just need to divide by the square root of a square plus b square. And that's it. This is actually the distance formula. Just make sure you don't screw up. Some students like do this instead of a and b, they say xa and ya. No, do not make this mistake. A is literally here and b is here. So make sure you don't screw up and write this instead. No. Okay. So yeah, keep that in mind. This is simply the distance formula. You can memorize it and apply it anywhere. It's very well known. Yeah. So yeah, maybe for example in some question, maybe you want to find a height, like the altitude. Then if you just have this point, then you can easily find the height. If you can just create the equation for this line and just this point, you can figure it out. Yeah. So these are basically all of the ideas I think I can like remember at least right now for computational geometry in the Cartesian coordinates, I mean. Of course, you might say, when do we use Cartesian coordinates? Like, will we use this in a math Olympiad problem? To be honest, you're not going to see Cartesian coordinates appearing a lot in Math Olympiad for many reasons. First reason, and it's mentioned in the book, that let's say like the coordinators or the problem setters, they know that all students know it from school, right? Computational geometry of the Cartesian coordinates. So they try to avoid like making their problem easy with Cartesian coordinates, and hence yeah, you're simply not going to see it a lot. However, in some cases actually you might be able to figure out like one solution using Cartesian coordinates. This happens in, let's say, from time to time. So yeah, you don't want to miss it. And that's the first idea. The second idea is actually it appears a lot in regional Math Olympiads, something like maybe AMC or like IOQM in India, or AMI even. Yeah, you're going to see Cartesian coordinates a lot, and some problems that have just synthetic solutions, you can also solve them with Cartesian coordinates, especially like when you have some question like this, like you have maybe a rectangle like this, and you have like then you take a midpoint maybe, and you draw this, and maybe like you intersect it with something. So yeah, clearly here you should just go with just Cartesian coordinates, right? You can, for example, take this as the origin and figure out everything else, right? Because you have just midpoints and you have intersections, perpendicularities. All of these are nicely handled with Cartesian coordinates. Yeah, so as I told you, in regional Math Olympiads, definitely you can use it a lot. And in more advanced, like national Math Olympiads, you will not see it a lot, but still in some actually problems you can use it from time to time. To be honest, like complex numbers, coordinates are used more often in these problems, but still you can just do that. And of course, we're going to discuss that in the examples. We'll do one example in the next video using Cartesian coordinates. So you're going to see it on a practice. Very nice. So now I just want to tell you when exactly to think about Cartesian coordinates. So the first scenario is when you have a prominent right angle. So why exactly is that? Because you're going just simply to pick this as the center, right? So for example, if you just simply have a right angle somewhere, then just try to take it as your O and see if it makes sense or not. Not all right angles are clean, but sometimes yes, especially when you have, as I told you, a rectangle, a square, something like that. You can always go for it and try to take this as your center and find everything else using this. So that's the first scenario, like when you have a prominent right angle. The other thing is, even if you don't have that, you can totally ignore the center and say the center is somewhere, like not a big deal, just take it like somewhere here. And let's say your question is like right here. It's not a big deal. Do not worry about always putting your center. Sometimes actually, when your question is all about maybe intersections, perpendicularities, parallelity, right? All of these are under like the domain of Cartesian coordinates. Parallelity, as I told you, all of these, collinearity, of course, all of these are nice. Okay, you might say, what if I have a circle? You know, like one circle is doable, not a big deal. Like only if you have just one circle, maybe. Like maybe you can take the center as the center of the circle. It really depends on your question. But like circles are not very cool. Like circles are usually like not very good. Also angles are not very good. So angles are not very good when you have like some angles, like this angle is 45. How can you express this using Cartesian coordinates? Not like you can sometimes figure it out, but not always. So I'm just telling you when to think of using Cartesian coordinates. Yeah, these are like the scenarios that you're most likely to counter. to encounter. Okay, yeah, with that done, I think we can move on to the next idea. So we're done right now with Cartesian coordinates. Our second idea is areas. Areas of what exactly? Of course, of a triangle. So we're just interested in finding all possible ways to find area of a triangle. Why exactly are we interested in finding areas of a triangle ABC right now? Well, of course, simply to find the area of the triangle, right? To calculate it, if you have a question about that. But actually, that's not the point here. The point is, we want to find a connection, or like how to find, let's say, if I give you the three side lengths, A, B, C, of a triangle, how to find the other things, like how to find the area, how to find the circumradius R, like capital R. How will you find the small r, which is the in radius, like how to find all of these using just ABC. So we want to find a connection between all of these. So we actually can do this using areas. So let's try to have a look. What do we know? Like we're going to list all formula for finding area. So of course the simplest one that you all know about is just like base times height, right? Half of A times H, where H is the height. So we all know about this. What do we also know? We actually have another nice one, which is half AB sine C. This is very nice. So let's say you have a triangle like this, and you have the angle C here. This is AB. Why is this true? You can just compare it with the previous one. So you have half A, that's the same. So clearly H should be equal to B sine C. And that's, of course, very easy to prove, because if you just drop the height, to A actually, it should be right, because the height from A, like this. If you want to figure out this height H, then clearly you can just look at this angle C. Sine C is just the height over B, over the hypotenuse. So yeah, that's it. So just B sine C actually is going to be H, right? So yeah. So we have this one. What do we also know? Well, of course, you can relate it to the angles if you want, using the law of sines, right? So for example, you can say half, and like for example, we know that A over sine A is equal to B over sine B, equal to C over sine C, right? So you might say that I can just get rid of B from here by replacing B with sine, like A sine B over sine A. So it's going to be half A square sine B sine C over sine A. Okay, so that's also one way. If you just know all the angles maybe, and you just know one side, you can find the area using that. Okay, here you have two sides and you have one angle. Here you just have maybe like you know the heights, and you know one side. I'm just giving you all possibilities. Okay, now let's say something else. Now, what if you have all the sides actually? If you have all the sides, it turns out that we have this nice formula that's called Heron formula. I'm going to write it here like Heron. It's well known, so no need for you to prove it. We will prove it, however. So it's S minus B, S minus, like this, square root of S, then like this product. Of course, here S is the semi-perimeter, so S is just A plus B plus C over 2, semi-perimeter. We're going to prove it in a second, but right now let's continue writing the others. So now we want to get the in radius involved, the in radius R, small r. So how can we get it involved? Well, actually it's going to be just SR, which is very lovely, just S times R, S the semi-perimeter times R. And the proof is actually very simple. You just draw, of course, to get R involved, you need to draw the like the incircle, right? So if we just have the incircle right here, let's say this is I. Of course, you can drop here to get R, also R, and also R. Now you can easily see that you can just cut this into 3 triangles. This is R, this is R, this is R, when you know the height for each one. So this triangle here is just going to be half AR, this one half BR, this one half CR. So if you just add them up, it's going to be half R times A plus B plus C, which is just S times R. So that's the proof for this one. Okay, so nice. So now we got R involved. Now, of course, if you want to figure out R using the others, then remember, you have this Heron formula that has only the side, and you have this SR. So from this equality here, you can figure out R by dividing this by S. Very nice. What about the circumradius, capital R? It turns out that also we can figure it out. So it's actually ABC over 4R. How exactly can we get this? Well, it's actually very easy. Remember, like we can play with like R using the law of sines. You should remember that A over sine A is equal to 2R, right? 2R. So yeah, you can simply just do this thing here. So replace 2R with A over sine A. So you have 2R here. So if you just replace that, it's going to be sine A over A. So A will cancel. Or basically, yeah, let's just say that A is 2R sine A. So replace that with that. Maybe I prefer that you replace C here. Let's replace C instead. So C is just 2R sine C. If I replace it like here, the 2R will cancel. It's just going to be AB half AB sine C. And guess what? We already got this here. So it is correct. And hence from here you can figure out R. So just like now R, and you have ABC over 4 here, and you can equate it to this and get your R. Very nice. Yeah, I think these are the main ones. Right now we just need to prove Heron, right? We have not proven this. All the others we have done the proof. So let's prove Heron. Of course, to prove Heron, since we have S minus A, S minus B, S minus C, this should remind you of something that we've discussed before, which is simply this configuration actually. You know, like S minus A, S minus B, S minus C appears here, right? This configuration. Because, let's actually draw, let's say here, going to prove Heron. So you just have a triangle, and you have the in circle here. If you just have I here, we just draw this thing here and drop this. We already know that this is S minus A. If you forgot why, then shame on you. Make sure to watch the previous videos, because we have done this before in chapter 3 basically. Anyway, right now we just have here a 90 degree, and we know that this is R, and we know this is I, and we know of course the angles. This is like an angle bisector, so we know that this is A over 2, and this is 90 minus A over 2, and hence we can find the relation between S minus A and R, right? And like using trigonometry, we can simply say that the tan, like S minus A is what? It's just the tan, or let's say R times tan 90 minus A over 2, right? Tan is just the opposite over like R, right? So the adjacent. So you can just replace it like this. So now we just want to plug in Heron, right? So Heron was this thing here, and we want to show that it's equal to SR. So that's, if you can show this, then we're done, because we have shown that SR is actually the area. So let's try to prove that. So of course now we know that S minus A, S minus B, S minus C, we know all of that. And we know actually S is their sum, right? S is S minus A plus S minus B plus S minus C, which is just the sum of these guys. So that means that root S minus A, S minus B, S minus C, we want to show it's equal to SR, which is equivalent to showing S minus A, S minus B, S minus C is equal to, if we just square both sides and take this and divide by S, it's It's going to be like this, right? And now we just I'm going to just repeat that back. Yeah, we just need to prove this, and now that's equivalent to showing r cube here, because I'm going to replace s minus a with r times tan 90 minus a over 2, and the other guys another 10 equal to r squared from here, and I'm going to replace s with their sum. So their sum is r this tan plus r this tan plus r this tan. So the r will cancel actually. We're just going to prove that this is equal to the sum of the tan, right? Like this plus this plus this. So as you can see, given these three, like if we just call them x, y, and z, so if I just call this as 90 minus a over 2, and the same for the others, then I just need to show that tan x, tan y, tan z is equal to the sum of the tan x plus tan y plus tan z. And actually, this is correct. Why? It's an identity, a trig identity. It's true for like when x plus y plus z, let's see here, x plus y plus z is what? Check it out, 90 plus 90 plus 90 minus a over 2 plus b over 2 plus c over 2. That's also 90. So it's when x plus y plus z is 180. This is true. Keep it in mind. Yeah, so we just can use this trig identity and we're done. So yeah, we're done. This is true. Okay, very sweet. So we have shown all the area. All the areas are like formula are true. And now again, why did we discuss the areas? We did not really discuss them just to find the area. No, we discussed them to find everything, to find r in radius. How? You apply Heron. Heron uses the three sides. Now you can find the in radius, you can find the circumradius, you can find the height, you can find the area, you can find the sine, like the angles, you can find anything you want. All just from areas. So areas are kind of a bridge that connects everything. And remember, you can also find the x radius, right? We have discussed this before, like the x radius RA. If you just like remember, like we said that RA over R is equal to S over S minus A. If you don't know, then also refer back to like the lesson in which we discussed the the x circle. I think it was lesson 1. Anyway, it's very easy. Just draw the x circle and the n circle and notice the similarity. You can just get this one. So yeah, so that means you can find everything, all the like lengths using areas. And yeah, now we're done with this idea. We can now move on to the next idea. The third idea that we want to discuss is trigonometry. And basically this will be our main focus actually in this chapter, because trigonometry is very, very useful in many problems. The idea is you can simply maybe transform some geometric question in which you need to find maybe some lengths or some ratios into just trig. If you transform it into just trig, you just can handle it using like the trig properties, trigonometry. And this is our main focus here. We want to discuss the trig properties and how to get trigonometry involved, like the sine and cosine involved in our question. So we already learned in the third chapter the main ideas, right? Remember, like the law of sines basically. So we have the law of sines. So you can simply say that a over sine A equals b over sine B, c over sine C equals to r, or in any triangle with side lengths a, b, c, and angles capital A, capital B, capital C, and r is the circumradius. So this is the first way to get trig involved. Just use the law of sines, right? That's the most powerful. We also have the cosine law, which is simply a square is equal to b square plus c square plus 2bc cosine A. It's kind of a generalization to Pythagoras, right? This is Pythagoras, but no, now you just need to like add this term. Of course, you can also write it as the cosine. Cosine A, isolate it and write it using the other stuff. So it's just equal to b squared plus c squared minus a squared divided by 2bc. Alright. So yeah, these are basically the main ideas on how to transform or get the trig involved in your question. Here, if you want to find ratios maybe of two sides, a over b, then you just transform it into sine a over sine b. Or you can just say a over sine a equals 2r. So replace a with 2r sine a. The other idea, in some questions you need to maybe show two lines are perpendicular. You want to do Pythagoras somehow. So you want to get the squares involved. So you just apply the cosine law. And you just apply cosine law and get this involved using the cosine law. These are basically the main ideas. And of course, if you have the three sides in a question, you want to find the angle, then you can figure it out, right? For example, you plug a, b, and c the value, and you get half. So cosine a equals half, and hence a is 60, right? Or maybe 120. So yeah, something like that. So these are basically the main ideas on how to get trig involved. Of course, do not forget the most important lemma out of these, which is like the ratio lemma, right? Ratio lemma, if you remember, you just have something like this. And you have like these angles, then you can just find BD over DC is just AB over AC times sine BAD over sine DAC. Do not forget this. Very powerful. In many questions, you just need to find this ratio. Then you just can say it's AB over AC times sine this angle over this angle. Keep that in mind. Of course, you can also replace AB over AC with sine C over sine B, right? So keep that in mind. You can always replace this by sine C over sine B. So you can transform it into pure trig, which is very powerful. Okay, keep that in mind. Alright. Now actually let's see the properties of trig, because trigonometry is all about angles, right? And you have tons of stuff. For example, sometimes you have sine maybe 180 plus x, or sine 180 minus x, or sine 90 plus x. How exactly can we find these? So to handle these, we want to introduce the idea of unit circle. What is a unit circle? It's simply a circle that has radius 1. So let us get this involved, and we just want to draw an x-axis and a y-axis here. So it turns out that we can here imagine this as the cosine axis and this as the sine axis. And any angle you have, maybe theta, you just draw here this is theta, and you can figure out actually x and like the x of this is the cosine theta, and the y of this is, so this is cosine theta and this is sine theta. Of course, this is 1, right? This point here is just 1, like 1 0, and this is 0 1. This is minus 1 0, and this is 0 minus 1. And it makes sense because we all know that sine and cosine are between 1 and -1, right? So it makes sense. So yeah, whenever you want to find any angle, then you just can take the unit circle and figure out that. Based on this, of course, you're going to have 4 quadrants, right? This is the first quadrant, and here you can see that both sine and cosine are positive in the first quadrant, clearly, because the x and y coordinates are positive, which is very nice. However, here in this quadrant here, the sine is still positive, but now the cosine becomes negative in the second quadrant. The third one, both of them are negative, and the fourth quadrant, the cosine is positive, but the sine is negative. So this is regarding the signs, you should know, depending on the quadrant. Yeah. Basically, we use these for these ideas. Also, you can actually get something nice, which is, what if you have minus theta? If you have minus theta, it's like you're rotating the other direction. So instead of saying this is 360 minus theta, you can just like imagine that you're going in the other direction, like this is theta. So now this is basically this represents the angle minus theta. So as you can see, for example, the cosine is still the same, right? So that means that the cosine of negative theta is the same as cosine of theta. So the cosine swallows the minus. It's an even function, right? However, the sine doesn't. As you can see, the sine, if you take here, clearly the sine and the other sign here, they are just flipped. So that means sine negative theta is negative sine theta, and hence sine is odd. So cosine is even function, sine is odd function. Keep that in mind. Okay, that's we just can get this from the unit circle. That's very lovely. What else can we get from here? We can get other stuff like, what about 180 minus theta, or pi minus theta? Pi here is just 180, but in red. So if you have this, then you can also do something similar. Clearly here, if you just do this, this is 180 minus theta, and hence this is theta, right? So again, you can see that they both have the same sign. Clearly, they have the same sign, but they have the cosine is flipped, right? So here you have the opposite. The cosine pi minus theta is minus cosine theta, while sine pi minus theta is equal to sine theta. So the sign of the supplementary is the same, but the cosine just gets flipped. The sign gets flipped. Keep that in mind. Okay, we can get all of this from the unit circle, which is very nice. And of course, you can figure out, the easy ones. Like you should always know the famous angles. Let's say this is sine, cosine. Just to remind you, tan should already be familiar with these. Here I'm going to write the angles. So you have pi over 6, pi over 3, which is like 60. This is 45. Of course, we have 0, pi over 2, pi. Yeah, you can easily, you should be able to just get these. So sine of 30 is just half root 3 over 2. And then you just, to find the tan, remember, to find the tan, you just flip these. So tan theta is just sine over cosine. And hence you can just divide this and get 1 over root 3. Here, the opposite. For 60, you just flip. Take this here, this here. So root 3 over 2, here it becomes half, and this gets flipped as well. Pi over 4, they are equal. They are basically 1 over root 2. 1 over root 2 and 1, because they are equal. For 0, the sign is 0. Again, if you get confused, just go here. So 0 means we're at this point, right? This is our point. This point, look at it. Because the x coordinate is 1, the y coordinate is 0. And hence 0, 1. Of course, now if you divide, then you get 0. Here, the opposite, 1, 0. And now here it's undefined, right? 1 over 0, like infinity. So that's undefined here. Yeah, for pi, again, pi is here. This point. Negative 1, 0. Negative 1, 0, 0. Okay, so these are just the famous ones. You should keep in mind. Do not forget the relation between sine and cosine. Sine theta square plus cosine theta square is equal to 1. And that's clearly obvious from here, because all the points will lie on the unit circle. So we know that the x square plus the y square should be 1. Yeah, so we have this thing here. Yeah, now we just want to discuss how to find, like, some stuff like this. Cosine 90 minus theta, or 90 plus theta, or 180 plus theta. These are a bit confusing. You want just to transform this into maybe like cosine theta, maybe plus or a minus, something like that. How to be able to get these easily? We want to explain this in a nice way. So first of all, I want to tell you that whenever you have 2 pi involved, 2 pi, you should know that all trig functions are periodic with period 2 pi. They have this period. And here's this does not affect. So here you should remember that it's periodic. So that means if you have sine theta plus 2 pi, then just get rid of the 2 pi. It's just sine theta. Same thing for cosine. Plus 2 pi is same, cosine theta. What if you have plus or a minus? It's again the same. You can just add and subtract 2 pi's. Does not affect. If you have 10 pi's, not a big deal. As long as it's a multiple of 2 pi, then yes, you can do that. So yeah, regarding 2 pi, life is easy. You might tell me, however, what if I have sine 2 pi minus theta? Well, remember, first of all, get rid of the 2 pi, subtract it. Now you get sine negative theta. For the negative, we already know from the odd-even property. So for example, sine is odd, and hence it's minus sine theta. So yeah, now you know how to handle 2 pi's. What about pi? Odd, I mean like odd multiples of pi. Okay, for odd multiples of pi, the lovely thing is the sign stays the same. The sine or the cosine, the trig function is still the same. So the function it's the same. However, you need to be worried about the sign. Here, like, you need to just know the sign. To know the sign, you just go to the unit circle. So figure out this using the unit circle. So this just should be your concern. Just worry about figuring out the sign. For example, let's say you are asked to figure out cosine theta plus pi. Remember, from what we discussed, you have a pi, then the cosine is still the cosine because the function is the same. So you immediately write cosine theta, which is nice. But now you need to figure out, is it a plus or a minus? How to figure out? Immediately go to the unit circle. Let's go. Unit circle is here. Okay, let's delete that. So if I have some theta here, what happens if I add a pi? If I add a pi to it, I'm going to be here. In what quadrant I am? This is the third quadrant. Here life is negative, right? Everything is negative here. So that means here the cosine is negative. Here it was positive. So you just flip it. Say minus cosine theta. Keep that in mind. Yeah, and so on. You can do the same for anything else. Let's take another example. Maybe let's say sine pi plus theta, or theta plus pi, just for the symmetry. Again, the same idea. The sign is still the same, the function is still the same, but you look at the pi, and like you need just to note plus or a minus. You go hit there, and it's actually the same here. We choose the same example. So you just do pi minus theta. Sorry, I mean pi plus theta. So that means you are in the third quadrant, and life here is a negative, right? So the sign is negative here, and hence you flip it. If you have, however, cosine pi minus theta, then again you have a pi, so the function does not change. You just need to figure out the plus minus. Again, you do the same thing. You go there. You're now in the second quadrant. So cosine is negative, so you flip it. Okay, so now life should be easy for you. So if you have, now you know how to handle 2 pi and pi. Now what about pi over 2? So what about 90s? Okay, to figure these out, it's also easy. Now you should just know that the function flip. So if it was a sine, it becomes a cosine. If it was a cosine, it becomes a sine. So simply just flip it immediately. Now to figure out the plus minus, like the sign of this, just go to the unit circle again. So unfortunately now you just need to be just careful here. Again, like this will be your main concern, but here you just flip. Again, let's take some examples. Let's say I told you figure out sine pi over 2 minus theta. First of all, you saw pi over 2, immediately you flip. You write cosine theta. But now you need to worry. Is it a plus or a minus? We just go to the unit circle quickly. If you have a theta and you take 90 minus theta, Clearly you're still here, right? By the way, always pick your theta as an acute angle, just for for you to simplify your work. Okay, so here you're still here, so life is still the same. Nothing changes. The sign is still the same. So I'm just going to keep it like this. However, let's say I told you maybe like cosine theta plus pi over 2. Again, you see pi over 2, then you immediately do what? You flip, say sine theta. Now you figure out the sign here. You just draw the unit circle and go ahead there. So theta plus pi over 2, so you're here. Second quadrant, the cosine is negative. So you just flip it. Okay, so hopefully now you know how to handle these. It should be easy for you. Now let's discuss the properties for trigonometry. These are very, very important. These are the hardcore actually that you can manipulate sine and cosine. So trig identities. Trig identities. So I'm going to give you two that you must memorize, keep them in mind, which are these: sine alpha plus beta. So if you just have the sign of like the sum of two angles, then actually it's easy. It's just sine alpha cosine beta plus sine beta cosine alpha. Yeah, you have this nice symmetry. Sine cosine, sine cosine. If you have cosine alpha plus beta, then it's cosine alpha cosine beta minus sine alpha sine beta. So be aware, when you have a sine, then they change. When you have cosine, then they are the same. Cosine, cosine, sine, sine. Here you have a minus, do not forget that. So these, you must memorize, these ones. Make sure you memorize. Now, I'm going to give you, of course, right now, imagine you have a minus. Like what's sine alpha minus beta? Now it's not a big deal for you. You just plug each beta with minus beta. And remember, you know how to handle the negative. So cosine is even, so it swallows this. Here, minus beta, the sign is odd function, so it becomes minus. So yeah, like I do not need to write you all the details, like alpha minus beta and alpha minus beta. You can handle it yourself. But now I'm going to write something that's very nice. You're going to use it a lot, which is the product sum identities. They're basically like this: 2 cosine alpha, cosine beta is equal to cosine alpha minus beta plus cosine alpha plus beta. That's the first one. You can also write like all others. It's going to be cosine alpha minus beta, minus cosine alpha plus beta. And you have 2 sine alpha cosine beta is equal to sine alpha minus beta plus sine alpha plus beta. By the way, do not forget that like you can get access to all of these on the Discord server. Like all of the formula we're writing here, you can make it as your reference if you want. Anyway, I'm going to teach you actually how to memorize these. I don't want you, in fact, to memorize it. I'm just going to tell you a quick way on how to figure these very quickly. So no need to memorize all of these. So how exactly can you keep all of this in mind? Of course, the importance of this is obvious. You just have a product, you transform it into a sum. You have a sum, you transform it into a product. And that's very, very helpful in some questions. So some questions you just have cosine plus cosine equals cosine plus cosine, and you want like to simplify, then you transform both of them to product, and hopefully maybe both of them are going to have this one term, so they will cancel. So you'll just end up with cosine equals cosine and you're done. Sometimes you have the opposite, cosine cosine. If you transform it into this, they will cancel, maybe this with another term there. So yeah, you're just going to play from, like, if you have this, go there. If you have this, go there. Yeah. Of course, again, now how to remember these? Well, remember that I told you to memorize these. And as you can see, these are the things that are repeating. This, And you know, of course, how to figure out this. We just mentioned that. They are just like appearing here, like here and there. So what do I want you to know to do? Just simply think of this cosine alpha plus beta and alpha minus beta. It's either a plus or a minus. Sorry, I should say the opposite, like this. It's either a plus or a minus. So if you have both of them are the same, like sine sine or cosine cosine, then you should use a cosine, because remember we just said cosine here gives you the same thing, the same. So if you have a product of the same pattern, sine sine cosine cosine, then just use cosine alpha minus beta, cosine alpha plus beta. Now you just need to figure out, is it a plus or a minus? You can quickly figure that out, because you know what's this and you know what's this, so it's easy for you. So now you can configure, like, get both of these easily. Now if you have sine and a cosine, so they are different, then of course you should go for a sine. So you simply just immediately say sine alpha minus beta, sine alpha minus plus beta, and then it's going to be a plus. So again, you just need to have this in your mind. Plus, you choose a cosine or a sine, depending on whether you have the same or the opposite. Here same, here different. Same, you go for cosine, otherwise you go for sine. And yeah, plus or minus, you just figure it out. It's easy. It will not take you even 30 seconds maybe. So yeah, so now you know how to handle these. Now they are just like some special formula. For example, what if you have sine double 2 theta? Of course you can actually just plug it there, right? We know it's theta plus theta, and in fact you just do that and you're going to get it's 2 sine theta cosine theta. What about cosine double? Again, you can just plug it, and in fact you're going to get cosine theta square minus theta square. This one you can play on it. For example, you know the cosine square is 1 minus sine square, right? So for example, you can just say 1 minus 2 sine square, or you can do the opposite, get rid of the sine. The sine square is cosine 1 minus sine square, so it's going to be 2 cosine theta square minus 1. Yeah, you can just play with that. So you can figure out 2 theta using theta. Of course, you can do the same for 3 theta actually. I'm not going to write it, but you know how to do this. You just like do a theta plus 2 theta and figure it out, apply the formula. You know 2 theta from here. So even if you have 4 theta, 5 theta, it's not a big deal for you. Yeah, these are basically the main ideas for trigonometry. Again, you're going to see this in practice in the next video once we do the practice part. But the idea is, as I told you, you have a question, a geometry question. You use law of sines, cosine law, or ratio lemma. You transform the question into sines and cosines, and then you just try playing with that using like all these nice properties that we know. Remember to use whenever you get confused, just draw the unit circle, and you can figure everything out. And yeah, we just consider how to get rid of 2 pi or a pi or pi over 2. Keep that in mind. And finally, the trig identities, make sure to memorize only these two. And the product sum identities, you know how to handle them from here. Of course, you might ask me that, wait a minute, sometimes I might have this in my question. Sine x plus sine y. How can I figure this out? Well, it's not a big deal. Remember, you know sine x plus y and sine x minus y. So just try to do this. So write x as a plus b, or alpha plus beta, and write y as alpha minus beta. And now you know how to expand this, right? So sine alpha plus beta is what? Sine alpha sine cosine beta plus cosine beta sine alpha. And the same thing for sine y. You can just alpha minus beta sine alpha cosine beta. So like one of them will cancel, so it's just going to be 2 sine alpha cosine beta. But now, of course, what was alpha and beta? Just solve the system of equations here. Add them up. You get 2 alpha is x plus y, so alpha is x plus y over 2, and hence replace this by x plus y over 2. Beta, you just subtract, and you get x minus y over 2. So yeah, that's it, we're done. So we figured it out, as you can see, very easily. We had a sum, just like make this alpha plus beta, this alpha minus beta, and figure that out. You already memorized these, remember? Just then see something will cancel, and just now figure alpha and beta, figure them out using x and y. So yeah, life is easy. You know how to transform sum into product and product into sum by just keeping this form in mind. Okay, so we're done with this idea. Okay, now we're discussing some nice theorems, just to end our video. The first one is Ptolemy's theorem. What exactly is this? The idea is very nice. If you just have a cyclic quad, say you have a circle here, just have a cyclic quad here. A, B, C, D. And I just draw the diagonals. Yeah. Then actually we just know that A, B, C, D is cyclic if and only if you have this nice relation. A, C, basically the product of the diagonals is equal to AB, CD plus AD, BC. That's it. So the idea is the product of the side, like opposite side, AB times CD, plus the product of the opposite sides, BC times AD, is equal to the product of the diagonals. Yeah, that's it. Originally, it's actually an inequality. It's like this Ptolemy's inequality. This is always true. But the idea is that the equality is true when it's cyclic. So yeah, keep it in mind. Okay, how can we prove this? As you can see, the question is about length tracing. We need to trace these lengths, and hence we can think about this nice idea. Why don't we transform this into trig? How exactly can we transform it into trig? Remember, you can figure out the angles. We have tons of equal angles here, and you can use the law of sines to get the sides into angles. How exactly can you get sides into angles? Using the law of sine. And in fact, remember that here all of them share the same r. So that means I can replace anything, any side, with just 2r sine the angle opposite to that to that side, right? Anyway, right now let's just get started by defining some angles. So first of all, to handle AB, we need an angle here, alpha 1 maybe. So for the arc AB, then for the arc BC, let's say alpha 2, then for CD, alpha 3, then DA just alpha 4. Remember that we do know a relation between them, so the sum of the alphas is just 180. So right now, just to prove this, just keep in mind that the sum of the alphas is just 180. Just I'm going to write pi. Let's keep that in mind. Okay, now we can start our trig bashing here. So what is let's find everything. So what's AB? Again, AB is what? Is 2r times sine alpha 1. By the way, we're going to apply the law of sine on everywhere. So here 2r, 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 2r. So the 2r will cancel. So we can just replace each thing with the sign of the arc. So AB sine alpha 1, BC like sine alpha 2, and so on. So yeah, let's just translate that. So what we want to show now is, I'm going to leave the diagonals for now, but sine AB is just going to be sine alpha 1. CD is going to be, what was it? CD is sine alpha 3. Again, if you're like confused what we're doing here, we're just applying the law of sine. Apply it on literally any triangle you want. And remember that all the triangles share the same r, and hence it does not really matter. That's why I'm just immediately saying that. For example, AB is just 2r times sine alpha 1. So yeah, let's continue. So we also have the other ones. We have AD, BC. So BC, we know it's sine alpha 2. And clearly AD is just sine alpha 4. Okay, now what about the diagonals? Well, guess what? It's the same. Not a big deal. For example, the diagonal AC, what's the thing? Like basically it's this arc, right? This angle. So what's this angle here? We know, remember, this is a cyclic quad, and hence this angle here is alpha 2, and this angle here is alpha 1. And hence I can just replace this with sine alpha 1 plus alpha 2. That's nice. So just sine alpha 1 plus alpha 2. The other one is also the same, sine. Let's have a look at it. BD is this. So you can say this alpha 2 plus alpha 3. So alpha 3 plus alpha 2. Okay, so that's what we need to prove. We need to show that this is true. But be careful for like some alpha equals pi. So now we can just replace maybe alpha 4 with pi minus alpha 1, alpha 2, alpha 3. You can just replace this alpha 4 with that. Anyway, for now, as you can see, the beauty of this trig bashing is we literally got rid of the whole geometry. The whole geometry, now we forget about it, and now we just need to prove this algebra, like algebraic relation. Given alpha 1, alpha 2, alpha 3, alpha 4, 4 numbers that add up to pi, just prove this. Again, no geometry, just algebra. That's the hardcore of that's the use and the point of the trig bashing. Okay, now let's just go ahead and prove this. How to prove this? Remember the trig properties that we discussed before. So you have a product, you have a product, you have a product. Then we just transform into a sum, right? So we have sine times sine. We already wrote that before. Sine times sine is just going to be again, if you forgot, then what do? You just remember they are the same type, and hence you just immediately write the general format: alpha minus beta, alpha plus beta. Is it either a plus or a minus? But here they are the same type. That's why we picked cosine, by the way. Is it a plus or a minus? You just figure it out quickly. So you know that this is going to give you everything plus. Here it's going to be cosine minus sine minus sine. Well, you want the sine to be there. So if you just add them up, no, that's bad. So you want to subtract, and hence it's going to be a minus. Yeah, so that's it. For example, now the sine alpha 1 as minus, sine alpha 1 sine alpha 3 is just cosine alpha 1 minus alpha 3 minus cosine alpha 1 plus alpha 3. So yeah, let's just replace everything like this. So this is going to be a cosine alpha 1 minus alpha 3 minus cosine alpha 1 plus alpha 3. Of course, times a half, but the idea is half, half, and a half. Everything cancels out. Okay, so now we can just add, and here the same thing: cosine alpha 2 minus alpha 4 plus, minus, let me put that there, cosine alpha 2 plus alpha 4. Here the same thing. It's just going to be cosine, the subtraction, so alpha 2 cancelled, so it's just alpha 1 minus alpha 3 minus cosine their sum. Well, guess what? What's their sum? Alpha 1 plus alpha 2 plus alpha 2 plus alpha 3. Yeah, so right now it's going to have actually 2 alpha 2 plus alpha 1 plus alpha 3. Okay, let's see. Does anything cancel now? Well, clearly yes. This cancels with this, which is very nice. Okay, but we still have like the other terms. What can we do now? Let's figure it out. Remember that we still know that the sum of the alphas is 180. Let's see. How can this help? So we have here alpha 1 plus alpha 3, here alpha 2 plus alpha 4. We know that these are supplementary. So one of them is cosine x, the other is cosine 180 minus x. But guess what? We know that cosine 180 minus x, remember you have a pi here, a pi, hence it's still the same. So it's cosine x. But what about the sine? Well, you can just draw the unit circle. I think pi minus x is here. So the cosine is negative, and hence it just flips. And hence, these actually cancel. This cancels with this. These two cancel out. Okay, very nice. So that means we just need to show that this is like, basically if I just move this to the other side, they add up to 0. Why do they add up to 0? Well, again, remember that their sum is pi, right? So we know that alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 is pi. Well, we have here 2 alpha 2. So what can I do here? I can just say that I can add a pi alpha 4 and subtract alpha 4. So it's going to be pi plus alpha 2 minus alpha 4. And cosine of that, you have a pi, so it's still the same. So it's just cosine alpha minus alpha 4. Again, draw the unit circle to figure out if you add a pi, you're going to be in the third quadrant, which the cosine is negative, hence it flips. So this flips, so cosine and minus becomes a plus. So now it's a plus alpha 2 minus alpha 4, which cancels out. Okay, super nice. So yeah, we're done. We have shown Ptolemy's theorem indeed is correct. Okay, that's it. So that's a very nice application for a trig. How can you use trig bashing to solve your geometry problem? Okay, we're done with that. We have shown Ptolemy's theorem, which is very, by the way, powerful, very nice. But actually, there is a nicer thing, which is you can actually figure out only one diagonal using using the others. So if you just have, let me just state that if you have A, B, C, D is cyclic, and you just have AB is A, BC is B, CD is C, DA is D, then guess what? You can figure out just AC alone. Previously we related AC times BD to ABCD, but now like previously we wrote this AC plus BD, that's what we did. But now I'm just going to tell you AC alone using ABCD, which is very powerful. So it turns out that this square is equal to the same thing, AC plus BD, this thing here, times AD plus BC divided by AB plus CD. And you also have the same thing for BD. Again, the AC plus BD is still the same for both, but now they just flip. So, just flip this and flip this. Divided by AD plus BC. Just find a way to memorize it. And yeah, you should be fine. So this is well known. It's called the strong form of Ptolemy's theorem. The strong form of Ptolemy's theorem here. Of Ptolemy's. To prove this, by the way, it's not a difficult task. You can actually here, because you have square involved, then you can go for the cosine law, right? So if this was AC, you can clearly go for the cosine law here and there. So if this was AC, this was B, this was D, then just go for the cosine law again. So as we said, you can just say that the cosine of B is equal to AC square. Let's just name this A, B, C, D. It's just what was the cosine law? Cosine B is just equal to A square plus B square minus AC square divided by 2AB. You also know that cosine D is equal to C square plus D square minus AC square divided by 2CD. But guess what? B and T are supplementary, and hence this is 180 minus pi, minus B. So if you just add them up, it's going to be 0. So just add these up, and that's equal to 0, and you just can get an equation. If you just like add these, you just get 0, and just like add them up and get the equation, and rearrange to isolate AC, and you will get this. Sorry, I mean this. Anyway, we have just this nice strong form of Ptolemy's theorem, and we're done with Ptolemy's. Right now, only one thing remaining, which is Stewart's theorem. Stewart's theorem. So yeah, you have just Stewart's theorem right now. What is this exactly? It's just if you have a nice triangle here, and you just have some CVN here, A, B, C, D. Then it tells you a nice idea, which is like how to find AD. Right? In many questions, you need to find AD. Maybe like find the median, right? Imagine that D was the midpoint. Then they ask you find the median. Or maybe it was an angle bisector. We need to find the length of the angle bisector. So usually like they give you what's BD and DC, right? You know, for example, the ratio BD over DC. If it was a midpoint, then you know it's A over 2, A over 2. If it was an angle bisector, you can figure out that using the angle bisector theorem. But the question is how to find AD. That's the struggle here. So guess what? Stewart just literally gives you that in a nice way. So let's just write the identity for that. So I'm going to just name this M and this N. I'm going to name, of course, this is C and this is B, right? Now, yeah, I'm going to name this D, and of course this thing is A, which is M plus N. So it goes like the following. Yeah, there is actually a nice phrase for you to memorize it. It's called like a man plus dad equals here bomb. Okay, sink. So it just a man and his dad put a bomb in the sink. Man, dad, bomb, sink. So now you can just take A as a common factor. It's Mn. Actually, let's write it as D squared plus Mn equals B square M C square N. That's it, and that's Stewart's theorem. And now, of course, your goal usually is to find D. So yeah, you can just isolate it. Divide by A, take Mn to the other side, and figure out D, just square root. And you can get like anything you want. The hardcore here is just to make sure you don't screw up. Make sure that B and M are opposite to each other. Don't make it like this. No. Remember, these are always opposite to each other. Opposite to each other. Bomb, B square M, sink, C square N. Yeah, the rest should be easy. Again, for example, if you want to find a median, let's do this practice. So if it was a median, then you just know that like M equals N equals A over 2. Then now you can just plug, right? So it's going to be D square A square over 4 equals M equals N. So take it as a common factor, which is A over 2. B square plus C square. Cancel the A. Move this to the other side. It's just going to be D square is equal to B square plus C square over 2 minus A square over 4. And that's it. You got. That's the median from A. MA square is equal to that. For me, I prefer to multiply by 2 and move it to the other side. So I actually memorize this like this. 2 MA square plus A square over 2 is equal to B square plus C square. Yeah, here like just like 1 1. Here you have MA and you have A. So A you divide by 2, M you multiply by 2. Anyway, you can just apply Stewart's theorem whenever you forget this. Yeah, so that was Stewart's theorem. Of course, the proof for Stewart's theorem, very easy. Notice that also cosine law, because everything is about squares. So cosine law here, cosine law here. These are supplementary, so they add up to 0. So you just get like a relation. There is another way to prove it, which is magically using Ptolemy's theorem actually. But let's just imagining here. This is our triangle. And this was originally the shape. So you just can continue this. If I just continue this now, you have this nice thing. So again, that was D, that was M, N, B, C, and the whole this thing is just A. So now we can apply Ptolemy's theorem to figure out this part here. So this part, you can figure it out, right? This part here, because you know that A times D plus that part is equal to B times this plus C times this. But now you might ask me, wait a minute, we don't even know these. How can we figure them out? Well, you can figure them out using similarity. You have here similarity. Remember, whenever you have a cyclic quad, then you have this nice similarity. So you can figure out this using similarity, and this using similarity, and then figure out this again using similarity. Then apply. Oh, sorry. Actually, you can just here also do power of point, right? Power of point. This point here, D. We know that M times N equals D times this. So in fact, this is just Mn over D. So this is Mn over D. Yeah, now you just need to figure out this using similarity, this using similarity, and then just apply Ptolemy's theorem. If you apply Ptolemy's theorem, you should be done. You will get, like after we found this using A, B, C, and D, and this one as well, and you just apply Ptolemy's theorem, and you will get the relation. Okay, I'm going to leave it for you guys. But yeah, that actually finishes the theory of this lesson. As a summary, in this lesson, we discussed all the theory of chapter 5, computational geometry. We started with Cartesian coordinates. We saw that it's not that a great tool for Math Olympiad, but still it's useful in regional Math Olympiads and in some actually more advanced problems where you can, like you have maybe a prominent right angle, as we said, to take it as your center, or when you have just like perpendicularities, collinearities, maybe intersections, these kinds of stuff, the standard stuff. And we just made like a review for like how to deal with basically coordinates, especially using slopes. Slopes are very nice. We discussed the Shorley's formula. We saw it's a very nice way to find the area. And if you just are experienced with determinant, then you can use it. Otherwise, just go for the normal collinearity idea. Two slopes are equal. We also saw the point line distance, which was a nice formula. Just make sure you memorize it. It's not that difficult. It saves you a lot of time. And we say, like we already said, when to use and when not to use. Do not use it when you have lots of circles or maybe lots of angles as well. Then we discussed areas. We saw that areas are a bridge to connect all the stuff, right? Like, for example, if you have ABC, you want to figure out the angles, you want to figure out the in radius, the circumradius, the height. You can find them all using the areas. Remember just Heron's formula, and then you can just depend on it to find everything else. Okay, then we discussed trigonometry. We saw that the hardcore of this chapter is about trigonometry, how to trig bash, and to get trig involved to your question, just apply the law of sine, or the cosine law, or the ratio lemma. These are our main ideas, and we saw how to deal with sine cosine using unit circle. Yeah, these should be remembered in your mind. How to handle 2 pi or a pi over 2. If you have 2 pi, then it's periodic, not a big deal, just remove it. If you have pi, then the function is still the same, sine, sine, cosine, cosine, but only the sign changes. I mean, like plus or a minus. You just look at the unit circle to figure it out. For pi over 2, you just flip the function. If it was a sine function, it becomes cosine function. It was a cosine function, it becomes a sine function. And again, plus minus, you look at the unit circle. Then we saw the trig identities. Just make sure to memorize these: sine alpha plus beta, cosine alpha plus beta. For the product sum identities, you can all get them just by looking at this. alpha minus beta, alpha plus beta. Either pick a cosine or a sine. Pick a cosine when they're the same, pick a sine when they're different, and then you just can figure out is it a plus or a minus. When you have a plus, like a sum, I mean you want to turn it into a product, then just make it alpha plus beta and alpha minus beta, and figure it out just like our first line here. If it was a product, we already considered how to do it. Remember these, like sine 2 theta and cosine 2 theta, the double. Not a big deal, you can just get them always. We had a Ptolemy's theorem. Ptolemy's theorem is just ABCD cyclic. Then you have this nice product of diagonals is equal to the product of like AB times CD plus AD times BC. We also have the strong form, which is to find AC just using the sides, and the BD using just the sides. They're both well known, so you can use them. Actually, here there is just a nice thing, which is look at the case when you have an equilateral triangle and a point on the circle. There is this nice formula. If you just apply, I want you to apply Ptolemy's theorem and tell me in the comments below what you get. Apply Ptolemy's theorem here and tell me what you get. Like if this was A, B, C, D, and this was P, just tell me what you get. Okay, so we saw how to apply trig to prove Ptolemy's theorem, which is very nice. Anyway, we'll do more practice in the next video. And we also discussed Stewart's theorem. We saw it's a very powerful tool to figure out this length. So imagine D was a median. You can figure it out. If it was, if I literally just give you some maybe numbers. So I gave you the sides and I gave you maybe this is 1, this is 2. Then you can figure out D. And if I give you anything like maybe like an angle bisector or anything, literally you can figure it out. Yeah. So we're done with the theory part. In the next video, we'll be discussing the 3 examples in the video, maybe something extra, we will see. So I hope you guys enjoyed the video. Please like, share, and subscribe to the channel, and share this video with your friends that are preparing for Math Olympiad. And see you guys in the next video.